Today, we're going on a journey, a really big one. We're going to explore the physics that connects the vastness of the cosmos to, well, the very ground beneath our feet. We'll start with these invisible forces that give our universe its substance, and we'll follow that thread all the way down to the raw, incredible power that can literally move our world.
And it all kicks off with a question that sounds simple, but is just unbelievably profound. I mean, just look around you for a second. The screen you're looking at, your own hands, this entire planet, all of it has mass. But what is mass? Seriously, where does this fundamental property of everything even come from? Well, the answer, it turns out, is hiding in the quantum world.
So here's our game plan. We're going to start with the secret of mass, then we'll catch some ripples in spacetime, then we'll see how we're learning to build with individual atoms, and finally, we'll see how all these ideas about physics play out right here when the Earth itself starts to shake.
All right, our first stop is one of the biggest, most celebrated discoveries in all of modern physics. We're talking about the particle that finally solved the mystery of mass.
You know, the search for answers like this always starts with these big, fundamental theories, our best attempt to explain reality itself. And the starting point for understanding mass isn't some particle you can see or touch, but actually an invisible field that fills absolutely everything. So I want you to try and imagine that the entire universe is filled with this invisible field of energy. It's everywhere. Some people describe it as a kind of cosmic molasses or thick syrup. This is the Higgs field. It's the stage where everything happens, but it's not the main actor.
No, the main actor is this particle, the Higgs boson. It's the physical piece of that field. So if you think of the field as a perfectly calm lake, the Higgs boson is like a tiny droplet of water that you can splash up from it. It's the tangible part of the field.
So how in the world does this whole thing grant mass? Well, it all comes down to interaction. As a particle, let's say an electron, moves through this Higgs field, it sort of attracts a little cluster of Higgs bosons. This interaction creates a drag, right? A resistance to being moved. And that resistance, that inertia, that is what we experience as mass. So the more a particle interacts with the field, the heavier it is. It's just a stunningly elegant idea.
But just because an idea is elegant doesn't mean it's easy to prove. Oh no. Finding this particle was a monumental, epic task. It took about half a century of searching and these enormous, mind-bogglingly expensive particle accelerators to finally do it. This incredible difficulty is actually what led to its famous nickname, the God particle.
Okay, now I want you to completely flip your perspective. We're going to zoom out, way out. From the unimaginably small, we're going to the unbelievably large. We're shifting from how tiny particles get mass to how truly massive objects can literally make the fabric of space-time ripple.
Just look at the sheer amount of time that passed here. Back in 1916, Albert Einstein came up with this idea that huge, violent cosmic events could literally send waves rippling through space-time itself. But for almost 100 years, that's all it was, a theory. Until 2015, when an observatory called LIGO finally detected one of these ancient cosmic echoes.
And the event that finally proved Einstein right, it was just the collision of two massive black holes. I mean, wow. And get this, the signal that finally reached us in 2015 had been traveling for 1.3 billion years. That's a faint whisper from a time before multicellular life was even a big thing here on Earth. The scale of it is just staggering.
So we've gone from the fundamental particles that make up everything to cosmic events that warp space-time itself. Now let's zoom back in, all the way back in, to a scale where we're not just observing the rules of nature, but we're actually starting to use them to build things, atom by atom.
And this is the world of nanotechnology. Just to give you a sense of scale, a single human hair is about 80,000 nanometers wide. So we are talking about building machines and materials on a molecular scale. It is engineering at the absolute smallest limit imaginable.
And the potential here is absolutely revolutionary. I'm talking about things like targeted drug delivery that can hunt down individual cancer cells, or ultra-efficient solar panels, even nanoparticles that can make our foods safer to eat. This is not science fiction anymore. It's about re-engineering our world from the atoms up, and you can see it's touching nearly every scientific field there is.
You know, whether we're talking about manipulating single atoms or watching black holes collide, it all boils down to understanding forces and energy. So now, let's bring that focus right back home to the most powerful force we experience right here on Earth, the immense, incredible energy that moves entire continents and creates earthquakes.
Okay, so when an earthquake happens, it releases all this energy in the form of waves. The first ones to arrive are called P waves, for primary waves. They're the fastest. They're compressional, kind of like sending a pulse down a slinky, and they can travel through both solid rock and the Earth's liquid outer core. Right behind them are the S waves, or secondary waves. They're a bit slower. These actually move the rock up and down, and it can only travel through solids.
So here's the key thing. Those P and S waves are traveling through the body of the Earth, but the violent, destructive shaking that we actually feel up on top, that comes from surface waves. Specifically something called regligh waves, which get created when those other waves hit the surface. And you can see why they're so destructive. They create this awful rolling motion, almost exactly like being on a boat in a really bad storm.
Now, to see how all these principles play out in a real and, frankly, terrifying scenario, let's take a look at the devastating Gorkha earthquake that hit Nepal back in 2015.
The main shock registered a powerful 7.8 on the magnitude scale. Now, it's really important to remember that this scale isn't linear, it's logarithmic. Each whole number is about a 32-fold increase in energy. So this wasn't just a strong quake, this was a truly massive, city-leveling release of energy.
And here's the detail that made everything so much worse. The quake's origin point, its hypocenter, was only 15 kilometers deep. For an earthquake this powerful, that is incredibly shallow. It meant all that seismic energy had a very, very short distance to travel before it hit the surface, which led to far more violent and destructive shaking for the people on the ground.
And the danger was nowhere near over. Just a few weeks later, a massive aftershock hit, a 7.3 magnitude quake. Now, this was not some minor tremor. A 7.3 is a major, powerful earthquake all on its own, and it compounded the initial devastation. It's just a grim reminder of these relentless tectonic forces that are always at play.
So, we've journeyed from the Higgs boson, giving particles their very identity, to gravitational waves telling us ancient stories from across the cosmos, all the way to the seismic waves that reshape our world in an instant. It all just goes to show you that underneath the surface of reality, there's this powerful, deeply interconnected physics at work. And it just leaves you wondering, what's the next layer we're about to peel back?